Welcome dear students, we continue with our topic composition of vectors. Last time we derived the formula for magnitude of R resultant of two vectors A and B magnitude of the resultant is a square plus b square plus 2ab cos of theta. Theta is the angle between A and B. Direction of R, the resultant, is given by b sin theta over A plus b cos theta. Here we have to keep in mind the vectors that we have added should be representing the same quantity. That is, if A is a force, B also is a force. If A is acceleration, B is also acceleration, and like that. So, the two vectors should represent the same physical quantity. If we have two forces, the formula become F magnitude of the forces, magnitude of the resultant force is F1 first force, F2 square, F2 is the second force, F1 F2 cos theta. For B we can write F2, for A we can write F1, for B we can write F2. Now, if we have two velocities, we will write the formula V is equal to V1 square plus V2 square plus 2V1 V2 and cos of the angle between the two velocities, and the angle or the direction is given by V2 sin theta V1 plus V2 cos theta. So, this will give us the resultant of the two velocities. Now, suppose we have two vectors, A vector and B vector. Now, when we add the two vectors, we are to see whether A plus B is equal to B plus A or not. If A plus B is equal to B plus A, we call the vector addition to be commutative. If vector addition is commutative, A plus B should be B plus A. So, now we use triangle law of vector addition. A plus B is equal to, resultant is given by the third side of the triangle taken in the opposite order. Now, if we complete the parallelogram with A and B, O, P, Q, S, OS is parallel to PQ and equal in length. So, OS can represent vector B also. Similarly, SQ is equal in magnitude to OP and parallel to its direction. So, this will be representing A. Now, from in the triangle OPQ, A and B are represented by OP and PQ, and the resultant is given by R is given by the third side taken in the opposite order. Now, if we take OSQ triangle, then we have B plus A. We take these two sides OS and SQ representing B and A now. So, the third side taken in the opposite again is OQ. So, this is equal to B plus A. So, what we have is A plus B is equal to R, and R is equal to R is given by the third side OQ. B plus A is equal to OQ. So, we can write A plus B is equal to B plus A. So, we can say vector addition is commutative. Now, second property of vector addition is, if we have A plus B plus C, if we for vector addition we have A plus B plus C, then we call vector product is vector addition is associative. Suppose we have three vectors P, or it is better to take A, B, C, now if we add these vectors, A plus B is given by the third side of the triangle. So, this is A plus B, and now we add to it C, and the resultant is given by O, P, Q, S. Resultant of the A plus B plus C is given by OS. So, OS gives us A plus B, first we add A to B and then we add the resultant of the two. So, OS is equal to A plus B plus C. Now, if we add B and C first, we can use triangle PQS in the triangle PQS we have B vector plus C vector. So, this vector PS is equal to B plus C. Now, in the triangle OPS, we have two sides of the triangle OP and PS taken in the same order. OS will give us the resultant if we take this in the opposite order. So, we can write the resultant is OS is equal to A plus B plus C. So, we have seen using triangle law of vector addition that vector addition is associative. Third property is if we have A plus B multiplied, combination is multiplied with lambda, then we can write this as lambda A plus lambda B. We can open the bracket like we do it in algebra. So, these are the properties of vector addition. So far we have discussed addition. Now, if we have to subtract a vector, subtraction of vectors. Suppose we are to find A minus B. What we do is we write A plus minus B. So, we add A and negative of B. Or we can write another, we can rename it, we can say negative of B is another vector C. So, this will become a simple addition of two vectors, like we have say this is A vector, this is B vector, and we are to add them. A vector this is B vector, C vector is a vector with the same magnitude, but making an angle of 180 degree. So, C is equal to negative of B vector. So, now what we do is we add A and C using simple vector addition. We can use parallelogram law or triangle law of vector addition. So, this diagonal gives us, diagonal of the parallelogram gives us the resultant. So, when we are to add to subtract a vector from another vector, what we do is we take the negative of vector and add it to the vector from which it is to be subtracted. We can write this as A plus C, or because C is minus B, so we have A minus B. So, this is simple. This becomes simple when we take minus B as negative minus B, we take as plus negative of B. We will use this subtraction of vectors while we will be studying relative velocities. We have defined resultant as a single vector that can give us the effect of more than one vectors. Now, if we have one vector, say we have one vector A, we want to find two vectors for which this single vector can stand for. It gives the effect of this single vector is to be divided into two vectors that give its effect when taken together. The process is decomposition of vectors or resolution of a vector into components or splitting of vector. Supposing we have a vector A, we want to find the components of A vector along A axis or along B axis. So, we take A vector, we take a line parallel to this line and equal in length arrowhead, that will give us A vector. Now, if we complete this parallelogram, let us say this gives us M A and this gives us M V. B, this axis, this is B axis, this is A axis. They need not be at right angle to each other. So, now this line is parallel to this line and magnitude is equal. So, we can write M B for both of them. From triangle of vector addition, O P A is equal to O Q, and from triangle of vectors we have O P plus O Q is equal to O P plus P Q, taken in the same order. O Q is in the opposite order. So, we can write this as M A, sorry, this should be N B, some other number which may or may not be equal to M. M A plus N B. M A is suppose a unit vector. We can, if we multiply this with M, it will become O P, and if we multiply this with N, it becomes Q P Q. So, now these vectors are components of A, vector. So, components of one vector are more than two or more than two vectors that give us the same effect as this single vector used to give us. Now, we come to the case when the two axes are perpendicular to each other. we call rectangular components. Components in that case are known as rectangular components. Suppose we have a vector A, we want to resolve this vector A into two components along x axis or y axis. A unit vector along x axis is a vector with unit magnitude and is directed along x axis. A unit vector along y axis is j. Similarly, if we take z axis, then this vector, unit vector along z axis is k. We will come to that in a short while. So far, we will be considering only two dimensional I and j vectors only. We have this A vector, it is represented by OP. OP has the same length as magnitude of A and same direction. Let us say the angle that OP or A makes with x axis is theta. So, if we drop a perpendicular from P on x axis, we have this triangle OMP. In this triangle, OP vector is equal to OM vector plus MP vector. OM and MP are taken in the same order, OP is taken in the opposite order. We can write this as this vector is say AX vector, OM gives us AX and ON gives us AY vector. Here we have N. PN is the right angle perpendicular on y axis. So, now what we have is OM is AX vector plus MP is MP and ON are equal and parallel. So, what we have is here we have AY vector. So, we have two vectors AX vector and AY vector are rectangular components of OP is A. So, AX and AY are the rectangular components of A vector. Now, as AX is along x axis, so AX vector, if we write its magnitude AX, we can write the direction by I unit vector. Similarly, AY vector is written as magnitude of AY multiplied with unit vector j along the y axis. So, now we have resolved A vector into two components. X component of A vector is AX, y component of A vector is AY. Now, this angle is right angle. So, the triangle OMP is a right angled triangle. So, AX over AX is OM, base over OP, hypotenuse, base over hypotenuse is cos theta. So, we can write AX is equal to A cos theta and AY over A is PM over OP and PM is perpendicular. Perpendicular over hypotenuse is sin theta. So, AY is equal to A sin theta. So, we can write A vector is equal to A cos theta into I unit vector plus A sin theta into J unit vector. Now, if we add the squares of AX and AY, we can write AX square is A cos theta square plus A sin theta square. So, this is A square cos square theta plus sin square theta. Cos square theta plus sin square theta is equal to 1. So, we can write magnitude of A is equal to square root of the sum of squares of the components AX and AY. So, if we know any of the three, we can find the other one. Now, what about the angle? If we know, we have tan theta is perpendicular over base. Perpendicular here is MP or AY and base is OM or AX. So, if we know the values of AY and Y component and X component, their ratio gives us tan theta. So, we can find from the tables the value of theta. If we have a vector, position vector of a point, P is the point. If we draw a vector from origin to this point, this is position vector R. Then we can write R is equal to X component of R is X I unit vector plus Y j unit vector. Now, this was the case for 2 dimensions. Now, in case we are to resolve the vector A along 3 rectangular components, we can write this as Ax I Ay j Az k. We have this vector OP represents the A vector from P we draw a perpendicular, it meets the xy plane at M. OM plus MP from triangle A, OP vector is equal to OM vector plus MP vector. OM vector we can resolve into two components along x axis and along y axis. So, these two components ON and OL. ON is along x axis and OL along y axis plus MP. We have used parallelogram law of vectors. Here we have used vector parallelogram law of vector addition. Now, ON is x component, OL is y component, and MP is z component. MP is parallel to z axis. So, we can write this as AX is the x component, AY is the y component, AZ is the z component of A vector. So, we can write A vector like this. Now, if we take the square of all these, AX square, AY square plus AZ square, we can write this equal to A square. We are generalizing the earlier relation A square plus AY square in 2 dimensions is equal to A square. In 3 dimensions, we have to add the third component also. Now, we have direction cosines. Direction cosines are cos of the angles made by the components with the A vector. L is equal to cos alpha, M is equal to cos beta, N is equal to cos gamma, L, M, N are known as direction cosines. Alpha is the angle between A vector and x axis. Beta is the angle between A vector and y axis. Gamma is the angle between z axis and A vector. Cos alpha is AX over A, cos beta is AY over A, cos gamma is AZ over A. Now, if we substitute these values, now if we are to take L square plus M square N square, we are to find the value of sum of squares of the direction cosines. We can write AX square over A square plus AY square over A square plus AZ square over A square. If we take A square as the LCM, we can write AX square plus AY square plus AZ square over A square. AX square plus AY square plus AZ square is equal to A square. So, we have A square divided by A square 1. So, L square plus m square plus n square is equal to 1. This is an other standard result. L square plus m square plus n square is equal to 1. L, m, n are the direction cosines. That is, sum of the squares of the direction cosines is equal to 1. This is a very important result that we will be using later on. For today, this is end of the lecture. Thank you.